Everything you think you know about light is wrong. Not slightly wrong. Not slightly wrong. Well, it's a simplification wrong. Fundamentally, deeply, beautifully wrong. You were taught that light travels in straight lines, that electrons orbit atoms like tiny planets, that when you flip on a light switch, photons shoot out like little bullets and bounce off walls into your eyes. Clean, simple, intuitive. None of that is what actually happens. The truth, the real truth, the one that took humanity until the middle of the 20th century to fully grasp, is so strange, so counterintuitive, so breathtakingly weird, that even the man who figured it out once said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." That man was Richard Feynman, and what he figured out didn't just win him the Nobel Prize, it gave us the most precisely tested theory in the history of human science. The theory is so accurate it's like predicting the width of North America to within the thickness of a single human hair. The theory is called Quantum Electrodynamics, QED for short, and today we're going inside it. Not the watered-down textbook version, the real thing. The actual mechanism behind how light and matter interact. The secret that most physics classes never quite get around to telling you. So buckle up, because by the end of this, the world will look different to you, literally. The problem that broke classical physics. Let's start at the beginning, not the very beginning of the universe, just the beginning of the problem. For a long time, physicists thought they had light figured out. James Clerk Maxwell in the 1860s showed that light is an electromagnetic wave. It oscillates, it spreads, it diffracts around corners, it interferes with itself. Wave behavior, all of it. Beautiful, elegant, mathematically precise. Maxwell's equations are still used today, and they work spectacularly well for most everyday situations. But then something strange happened. In 1905, his miraculous year, Albert Einstein looked at a phenomenon called the photoelectric effect and noticed something deeply troubling about Maxwell's picture. When you shine light on a metal surface, electrons get knocked off. Straightforward enough. But here's what's weird. The energy of those ejected electrons doesn't depend on how bright your light is. It depends only on the color of the light, the frequency. Dim blue light knocks off fast electrons. Bright red light, no matter how intense, knocks off nothing at all. That makes no sense if light is a wave. A bigger wave should pack more punch, right? If you've ever been knocked over by a large ocean wave, you understand the intuition. More amplitude, more energy delivered. But that's not what light does. Einstein concluded, reluctantly, even he found it uncomfortable, that light comes in discrete packets. Quanta, what we now call photons. Each photon carries an amount of energy determined by its frequency, and when it hits an electron, it either has enough energy to knock it loose or it doesn't. No amount of extra photons of the wrong frequency will help. So light is a particle, except of course, it also demonstrably acts like a wave. The double-slit experiment proves it. Send photons through two slits, one at a time, and they build up an interference pattern on the screen behind. The unmistakable fingerprint of wave behavior, even though you're sending them individually, one by one, with nothing to interfere with. So light is a wave and a particle, at the same time, somehow. Welcome to quantum mechanics. Leave your intuitions at the door. Feynman enters the picture. Richard Feynman was, by every account, something genuinely unusual. Not just a brilliant physicist, there are plenty of those, but a man who seemed physically incapable of accepting an explanation he didn't truly, viscerally understand. He needed to feel it, to play with it, to rebuild it from scratch in his own mind, until it clicked in a way that satisfied not just his intellect, but his gut. He grew up in Far Rockaway, New York, the son of a uniformed salesman who taught him, above all else, to distinguish between knowing the name of something and knowing the thing itself. His father would point at a bird and say, "I can tell you that bird's name in 15 languages, but I still don't know anything about the bird." That distinction between label and understanding became the engine of Feynman's intellectual life. When he turned his attention to quantum electrodynamics in the late 1940s, the theory was a mess. Calculations kept spitting out infinities, nonsensical answers. The mathematical machinery was breaking down. Other brilliant physicists, Julian Schwenger, Sinatiro Tomonaga, were working on fixes involving sophisticated mathematical renormalization. Their approaches worked, technically, but they were extraordinarily complex. Feynman looked at the same problem and did what he always did. He drew pictures, not decorative pictures, functional ones. Diagrams that represented physical processes. Diagrams that turned complex integrals into something you could almost see. What we now call Feynman diagrams weren't just a visual aid. They were a completely new way of thinking about particle interactions. But to understand why those diagrams matter, we first need to understand the genuinely jaw-dropping thing Feynman discovered about how light actually travels. The path integral, light, doesn't choose a path. It takes all of them. Here's the thought experiment that cracks QED open. Imagine you're standing in a room with a flashlight, and across the room there's a mirror, and you want to understand how the light gets from the flashlight to your eye after bouncing off the mirror. In classical optics, the answer seems obvious. Light travels in a straight line from the flashlight to the mirror, hits the mirror at a specific point, the point where the angle of incidence equals the angle of reflection, and travels in a straight line to your eye. Neat, predictable, a single path. Now, here's the question Feynman asked, and it's the question that changes everything. How does the photon know which path to take? Think about it. The photon leaves the flashlight. The mirror is sitting there. How does the photon, before it arrives anywhere, figure out the single correct point on the mirror to bounce from? The classical answer is essentially because the laws of physics tell it to, which, when you think about it, isn't really an answer at all. It's just restating the observation. Feynman's answer was different, radical, almost absurd sounding at first. The photon doesn't choose a path. It takes every possible path simultaneously. Stop. Think about that for a moment. Every conceivable path. A path that goes to the mirror's left edge. A path that arcs up to the ceiling first. A path that somehow swings around behind you, goes outside, orbits the building, comes back through the window, and then hits the mirror. Every conceivable path you could draw between the flashlight and your eye, including the completely insane ones. The photon is taking all of them, but we only see light arriving from one direction. We observe what looks like a single path. So how does the madness of every possible path produce the order we observe? This is where Feynman's genius shows itself. Each possible path the photon takes comes with what Feynman called a probability amplitude, not a probability amplitude. A quantity that has both a size and a direction, like a little rotating arrow. You can think of it as a clock hand. As the photon travels along any given path, this clock hand spins. It spins at a rate proportional to the energy of the photon. Now, to find out whether a photon is likely to arrive at a particular location, you add up all these little rotating arrows, one for every possible path. You sum them all. What happens when you add up a huge number of arrows pointing in random directions? They cancel. The arrow pointing left gets canceled by an arrow pointing right. The crazy paths, the ones that go around the building and come back through the window, contribute arrows spinning all over the place. Chaos. They wash each other out. But near the classical path, the straight line path, the law of reflection path, something different happens. The paths that are close to the classical trajectory have clock hands that are all pointing in roughly the same direction. They add together constructively. They reinforce each other. Their contributions survive. So the path we observe, the classical textbook path, isn't the only path the photon takes. It's the path near which all the quantum contributions add up rather than cancel. The rule of reflection, the rule of refraction, the straight line travel of light. None of these are fundamental laws that light obeys. They're emergent behaviors. They're what you get when you add up the contributions of every possible path and find out which one dominates. This framework is called the path integral formulation of quantum mechanics, and is one of the most beautiful ideas in the history of physics. Photons and electrons, the dance that makes everything all right. Now we get to the heart of QED, because QED isn't just about how photons travel. It's about how photons and electrons interact with each other. And that interaction turns out to be the foundation of almost everything in the physical world you experience. Every time you see something, a photon has entered your eye. Every time you touch something and feel resistance, Electrons in your fingertips are electromagnetically repelling electrons in the object. Every chemical bond and every molecule in your body is a consequence of electrons interacting via photons. The light from the sun, the warmth of a fire, the glow of your phone screen, all of it, at the deepest level, is electrons and photons doing a very specific dance that QED describes. So what does that dance actually look like? In QED, there is essentially one fundamental interaction, just one. An electron moves through space-time, and at some point, it absorbs or emits a photon. That's it. That single interaction, combined with the path integral approach and applied repeatedly, generates everything else. Reflection, refraction, the photoelectric effect, atomic energy levels, chemical bonds. All of it falls out of this one basic vertex. Now here's where it gets interesting, and also where it gets genuinely strange. The photons involved in most everyday electromagnetic interactions are not the kind of photons you can detect with your eyes or a camera. They're what physicists call virtual photons. And understanding virtual photons means grappling with something that even working physicists sometimes debate how to interpret correctly. You know the Heisenberg uncertainty principle. Most people have heard of it. You can't know both the position and momentum of a particle with perfect precision simultaneously. But there's another version of the uncertainty principle that's equally profound and less often discussed, the energy-time uncertainty relation. It says that for very short periods of time, energy conservation can be temporarily violated. A particle can briefly borrow energy from the vacuum, energy that doesn't exist by any normal accounting, as long as it pays it back fast enough. Virtual photons exploit this loophole. When two electrons approach each other and repel, here's what's actually happening at the quantum level. One electron emits a virtual photon. This virtual photon carries energy and momentum. It's real enough to cause effects, but it exists only briefly in the space between emission and absorption. The second electron absorbs this virtual photon, and in doing so, it receives a momentum kick, a push, repulsion. But wait, you might be thinking, if a virtual photon pushes the electrons apart, how do electrons also attract protons? How does electromagnetic attraction work if photons are doing the pushing? This is a subtle point, and it trips up a lot of people. A naive billiard ball picture, where a photon flies between particles like a tiny baseball and pushes them apart, doesn't really work for attraction. The real answer lies in the quantum mechanical nature of momentum. Virtual photon exchange doesn't work like macroscopic collisions. The mathematics of QED allows virtual photons to mediate both attraction and repulsion depending on the charges involved. The photon carries information about the electromagnetic field, not just a single push. Think of it this way, and this is an analogy, not a perfect description. Imagine two people in rowboats on a lake. If they throw a ball back and forth, the act of throwing pushes each boat away from the other. That's like repulsion. But now imagine a strange kind of boomerang ball that somehow curves around and pulls the boats together as it's caught. The virtual photon is more like that. It's a quantum mediator of force, and the mathematics determines whether it mediates attraction or repulsion based on the specific charges involved. Probability, not certainty. Why the quantum world refuses to commit. Here's another thing. QED gets absolutely right, the classical physics gets wrong. When you shine a beam of light on a piece of glass, most of the light goes through. Some of it, about 4%, reflects off the surface. You can see this for yourself. Look at a window at night from inside a lit room. You see both through the glass and your own reflection. Two things at once. Classical wave theory has an explanation for this. Partial reflection. The wave partially reflects and partially transmits. Fine. But what happens when you send photons one at a time? Each individual photon either reflects or transmits. It doesn't partially do both. It makes a choice. And the choice is random. Not random in a hidden way. Not we just don't know the real cause. Genuinely, fundamentally, irreducibly random. Feynman himself was emphatic about this. There is no deeper mechanism. There is no hidden variable. The photon doesn't have a secret property that determines which way it goes. The universe simply decides, with a probability of about 4% for reflection and 96% for transmission. QED lets you calculate that 4% with extraordinary precision. But it cannot tell you what any individual photon will do. Nobody can. The universe is not a clockwork machine running on predetermined tracks. At its most fundamental level, it is a probabilistic entity, and the probabilities are all we get. Feynman described this situation with characteristic directness. He said that the question, "But how does the photon decide?" has no answer. Not because we haven't found the answer yet. Because the question itself assumes a kind of determinism that nature has specifically, provably declined to possess. And here's what makes this even more extraordinary. QED's probabilistic predictions are not vague approximations. They are the most precise predictions in all of science. The magnetic moment of the electron, a measure of how the electron responds to magnetic fields, has been calculated using QED to 11 decimal places of accuracy. Experimentalists have measured it to 11 decimal places. The two numbers agree. 11 decimal places. To put that in perspective, that's like predicting the outcome of a dice roll with a precision that would let you predict not just which face lands up, but the exact position of every molecule of air that touched the die in flight. A theory that is fundamentally probabilistic produces predictions of extraordinary precision. Not predictions of what individual events will do, but predictions of what averages and frequencies will look like. And those predictions are so accurate they take your breath away. The deeper strangeness, self-interaction, and the infinite. There's one more layer of QED that we should visit because it leads somewhere philosophically profound. One of the problems that plagued early quantum electrodynamics was this. If an electron can emit and absorb virtual photons, what happens when the electron emits a virtual photon and then absorbs its own virtual photon before it interacts with anything else? The answer, when you try to calculate it, is infinity. The electron interacts with its own electromagnetic field. And because the field becomes infinitely strong as you approach a point particle, the electron's self-energy, its interaction with itself, blows up mathematically. The calculation returns nonsense. The solution to this problem is one of the more controversial and philosophically uncomfortable things in modern physics: renormalization. The basic idea, without the mathematics, goes like this. When we measure the mass of an electron, we're measuring the total electron, the bare particle plus all its self-interactions, all its virtual photon emissions and reabsorptions, all the infinities included. So instead of trying to calculate from a bare infinity-free starting point, we absorb the infinities into the measured quantities. We say whatever the bare electron mass is. We define the physical measured electron mass to include all those infinite corrections. Then we work from there. This sounds like cheating. Feynman himself called it sweeping infinities under the rug in one of his less diplomatic moments. Even after winning the Nobel Prize, he remained troubled by it. He suspected that renormalization was a mathematical trick that papered over a deeper problem we hadn't yet understood. He might have been right. The deepest questions of QED remain open. How to unite it with gravity? What happens at extremely high energies? Whether renormalization is a temporary scaffolding or a permanent feature of the theory. These are the questions that keep physicists awake today. But what's remarkable is that despite this theoretical discomfort, the predictions work, the infinities are controlled, the theory calculates, and the answers match reality with a precision that no other scientific theory in history has matched. The world you're actually living in. Let's bring this home. You're sitting somewhere right now, reading or listening. Light is entering your eyes. Your clothes are touching your skin. The air molecules in your lungs are bumping against each other and against the walls of your alveoli. Every single one of those interactions, every photon that enters your eye, every electromagnetic repulsion between your clothes and your skin, every molecule bouncing against another molecule is, at the quantum level, an exchange of virtual photons between electrons. You are swimming in a sea of virtual particles right now. Particles borrowing existence from the vacuum, flickering into being for unimaginably tiny fractions of a second, carrying the electromagnetic force between the particles that make up your body and the world around it, and then vanishing again. The apparent solidity of the world, the hardness of the floor, the warmth of sunlight, the ability to pick up a cup of coffee, is made entirely of electromagnetic repulsion mediated by virtual photons. There is no actual contact happening anywhere. When your hand touches a table, the electrons in your hand and the electrons in the table never touch. They never get closer than a certain distance before the virtual photon exchange becomes strong enough to push them apart. That pushing is what you interpret as touch. The floor is not solid. It is a probability distribution maintaining its average position, very, very reliably. And the light you see, the photons arriving in your eyes right now, each one of those photons, according to QED, took every possible path between its source and your eye. It went to the moon and back. It took a detour through the center of the Earth. It explored every corner of the universe. All of those paths contributed their little rotating arrows, and all of those arrows added up, and what survived the cancellation was the slim set of paths near the classical trajectory. That's the path you observe. That's the light you see. The universe is not lazy. It doesn't take shortcuts. It tries everything, all at once, and only the consistent parts survive. The beauty of not knowing. Richard Feynman once gave a series of public lectures on QED, accessible lectures, intentionally stripped of mathematics, aimed at anyone curious enough to pay attention. He was doing exactly what he always did, refusing to accept that important ideas belong only to specialists. At one point in those lectures, he said something that has stayed with physicists and non-physicists alike for decades. He said that he was going to describe to his audience the way electrons and photons interact in plain English, which means I'm going to be lying to you a little bit, but the lies will get less and less as we go on. That humility, that acknowledgement that our models are always approximations, always partial, always pointing towards something we haven't fully grasped yet, that is the soul of good science. And it's especially the soul of QED. We have this theory that is more accurate than any other theory humanity has produced, and we also know it's incomplete. It doesn't include gravity. It doesn't explain why there are exactly the particles there are, with exactly the masses they have. It doesn't tell us what an observation really is, or why the quantum world gives us probabilities rather than certainties. These are not small gaps. They are enormous, yawning mysteries sitting right at the center of our best understanding of reality. And isn't that wonderful? Not unsettling, wonderful. Because every one of those gaps is a door, and behind every door is a room we haven't entered yet. A room full of ideas that will make the world look different again, the way QED made the world look different from classical physics, the way quantum mechanics made the world look different from Newtonian mechanics. There is a ceiling to our knowledge right now, and we can see it. We know where the current understanding runs out. That's not a failure. That's a map with blank spaces at the edges. Just like the old cartographers used to draw, and into those blank spaces, the honest inscription, "Here be dragons." Feynman was one of those rare people who could look at a dragon and feel not fear but delight, who could stare at the deepest mystery in physics and say, essentially, look at how beautiful it is that we don't know. That's what it means to be a scientist in the deepest sense, not to possess answers, to be genuinely, passionately in love with the questions. And the question of how light interacts with matter, a question that took a Nobel Prize to even partially answer, a question that still holds surprises. That question is one of the most beautiful ones the universe has ever given us to play with. Go play with it. The photons are already taking every possible path. Some of them are passing through your hand right now. Some are bouncing off the back of your eye. Some are on their way to you from a star that no longer exists. All of them are doing the most astonishing thing, being real in a universe that runs on probability, building the solid, warm, visible world out of chance and interference and the ghostly arithmetic of quantum amplitudes. If that doesn't make you look up from what you're doing and feel something like awe, something like gratitude for being a conscious creature in a universe strange enough to have photons and minds both in it at the same time, then nothing will. And if it does make you feel that, welcome to physics. The door's always been open. You just needed the right light to see it by.